Welcome to this video. We are going to learn about simple harmonic motion and Hooke's law. What happens if you take a spring and you stretch it to the right? Okay, well imagine you grip the spring, or maybe it's not you, but Voldemort. What kind of a hand is that? So you grip that spring and you pull to the right with some force. What does the spring do? It resists that stretching. In particular, it pulls back to the left. So a force is generated in the spring, pulling the end back to where it was before. And in general, this is true for springs. They resist stretching, they resist compression. So this is summarized in Hooke's law, which says that the spring force is equal to minus a constant times x, and x is the displacement from the normal relaxed position. And this is Hooke's law. This is an equation. And what it says is that there's a spring force generated which opposes the displacement. Opposes. Here's what that means. Opposes. And we're going to look at the negative sign. If you take this spring and you stretch it to the right from the normal resting position, you've just given it rightward or positive displacement. And the force pulls back toward displacement. The force pulls back toward this normal position, this relaxed position. So the force is going to be leftward, negative. On the other hand, if you take this spring and you compress it to the left, if you push it to the left with some displacement, that means you've given it a negative displacement because leftward is negative. And this thing pushes back. The spring wants to go back to where it was, back to this relaxed position. So you generate a rightward force in the spring. Rightward because, rightward, which means it's positive, the force. So what do we notice? The sign of the displacement and the sign of the force are always opposites. And this makes sense. I mean, after all, imagine there was not a negative sign. We would have something like maybe negative 15 newtons as the force, and then we would have a positive displacement. See this? Just like the first example, positive displacement, negative force. K is a constant, and the constant will always be positive in this case. So because the constant is positive, you need a negative sign here, or else the left side and right side are not equal. Without a negative sign, you have something negative on the left and something positive on the right, and those can't be equal. So the negative sign is there because the force and displacement are always in opposite directions. So here's our answer. The spring force and the displacement have opposite signs. One is positive, the other is negative. And those arrows point in opposite directions. That's why there's a negative sign in the equation. Now, lots of different objects move back and forth repetitively. A grandfather clock is one, the pendulum inside. So imagine you've got that grandfather clock, and you can open up the little door on the front, and you look inside and watch what happens. And here's what you see. It goes back and forth, right? And back and forth, just like this. The pendulum is oscillating, we say, or swinging back and forth about a center position. So the center position is shown with this dotted line. That oscillatory motion is called simple harmonic motion. And this pendulum is an example of a simple harmonic oscillator. Right? So you might think, what a random example, a grandfather clock. But we're going to see that there are many applications of this. So the pendulum, a guitar string, rubber ducky, when you bob it up and down in the bathtub. On your computer, the speakers have this type of motion. A car without shock springs can oscillate with simple harmonic motion when it goes over a bump. Even atoms can display this oscillatory motion. Now, these things all involve motion along a fixed path, back and forth, back and forth. But there's something deeper connecting them. Every single one of those is defined, the motion follows this equation. The net force is equal to negative a constant times the displacement. Another way we could write this is we could say the acceleration is negative a constant times the displacement from the center. This is the defining equation for simple harmonic motion, and whenever an object is meeting this equation, it is in simple harmonic motion. Now, of all of the examples that I showed you, the simplest one is actually just a spring oscillating back and forth. Simple harmonic motion is what you have whenever this equation is true. Whenever the net force, in fact, is equal to negative a constant times displacement. Here's Hooke's law again. So imagine you take a spring, horizontal spring, and you attach a block to the end. Right? There's the ground, and here's the block. This is a frictionless surface, so imagine there's no friction at all. There's our center position. We'll just use the left side of the block to mark the center of the motion. That's its resting position. If you take this block, stretch it out, so now the left edge of the block is over here, and you hold it there, is it in simple harmonic motion? Well, let's see. Your hand is pulling the block to the right. This spring is pulling the block the other way because you just stretched that spring to the right, and so the spring pulls back to the left. And then there's gravity pulling down, as well as the normal force, the perpendicular force of the surface against the block. And these two cancel out, normal force and gravity. These two cancel out. They all cancel out, and the net force is 0. So, is it in simple harmonic motion? No, because we do not satisfy this equation. You need some positive constant here in order to have simple harmonic motion. So the net force will not restore this block back to the center position. You're not going to get back and forth motion out of this thing. There's no oscillation. To oscillate, you need to pull it to the right and then have it be pulled back to the left and have it actually move along that that back and forth path. So imagine then you let go of the block. When you let go, the force of your hand disappears. And now the net force is simply this spring force because the other two cancel and there's no friction. So the spring force is equal to minus a constant times the displacement. And yes, we see that we now satisfy the equation for simple harmonic motion. This is in simple harmonic motion. There will always be a net restoring force pulling the block back to its center position. So let's watch this in action. Here's the block at its natural resting position, the relaxed position. I'm going to click on the block and pull it to the right. Let's get this going. And pull it to the right, and you're going to see I'll let go and it'll start oscillating back and forth. Whenever the block is being pulled to the right, the spring force pulls it back to the left. And whenever the block is over on the left from its center, the spring force pushes it back to the right. Now, something interesting that I want you to watch for is this. Where is the block going fastest and where is it stopped? Right? Where is the block stopping? Where is it going the fastest? Okay, let's watch again. The block is going the fastest when it is at the, where do I let it go? The block is going the fastest when it's at the middle and it is stopped at the edges. So watch again. When it gets to the edges, it stops. It just stopped, stopped. Every time it gets to the edge, it stops and turns around. Now, what about in the middle? When it's in the middle, it's had time to accelerate all the way toward the center because after all, it's getting pulled toward the center, so it accelerates toward the center. And then when it gets to the other side, the block starts slowing down and eventually it stops. And then it accelerates toward the middle, and at the middle, it's going really fast again. Right there, it's going really fast in the middle. But as soon as it passes through the center, it slows down because it's getting pulled the other way. So it's going fastest in the middle. Can you see that? Right about there is the fastest. And it stops at the edges. So let's summarize what we just saw in the simulation. Here's the block, and I've put a dot in the middle so that we can use the dot as our reference for the system. The system was oscillating to the right and to the left. So here it is when it was displaced really far to the right. So that arrow shows its rightward displacement. And then here's the block when it's displaced to the left at the edge of its path. And that arrow shows the leftward displacement. So what did we say? Well, the displacement is at a maximum here because it's all the way to the right edge of its path. Here, the displacement is 0 because it's at the center of the path. And then down here, we've been pushed all the way as far as we go, but to the left. So we have a very, very negative displacement, making it the minimum displacement at this moment. And then what about speed and velocity? We said that at the edges of the path, the velocity is 0. At the middle, the block is going the fastest. Now, sometimes the block is going really, really, really fast to the left, which means it has a huge negative velocity. Other times, the block is coming back and moving to the right through the middle, and so the block has a really, really, really huge positive velocity. So when you are at the center, the velocity is either going to be a maximum or a minimum, either a huge positive value or a huge negative value. And when I say huge, I mean relatively huge. What about force and acceleration? Here are the equations that we know for force, net force, and then here's the simple harmonic motion equation for acceleration. So let's think about this. When we have a huge displacement, we have a huge net force, but they're pointed in opposite directions. So at this moment, we have a huge rightward displacement, so we will have a huge leftward net force. And that means the object will be accelerating very strongly to the left. A huge leftward acceleration means it's a minimum acceleration. In the middle, the displacement is 0, so there's no net force and there's no acceleration. Because when you multiply the constant times 0, you get 0 for the acceleration. And lastly, down here at the bottom, our displacement is huge and leftward. Therefore, it's going to be pushed really, really, really hard to the right in the opposite direction. If the force is a huge positive value, then the acceleration will be a huge positive value as well. And that will be our maximum acceleration because it's positive and it's a big value.